theoretical. All these research methods are complementary of each other. And for the verification of result, we need the help of other methods. So individually, if someone is working experimentally, another one is mathematical modeling, and third one is the computational research, then if individually they are working, then the situation is like this. A big project one can start, but the limited part of that project can be studied individually by either experimentalist or computationalist. So if we want to study complete that project as a whole in a complete manner, then there is a need of teamwork, and where that experimental as well as computational research can perform simultaneously. Outline of my talk. So I will start from the glimpse of density functional theory, and yesterday, just the day before yesterday, Dr. Ravi Pandey was there, and he has mentioned so wonderful result in his presentation, and that was mainly based on density functional theory, and he has assigned me a job to introduce you the density functional theory and some tools and some applications of this density functional theory. This is nowadays this density functional term, the theory term is not new, but we will go some detail in this lecture, this presentation, and some computer experiments that the work related to this density functional theory or this computational work are referred as computational computer experiments, and for which we are using Siesta. And I will also give some glimpse how to start material research using DFT, and as in the title I have mentioned that I will include some terms related to photovoltaic application. So how one can use this DFT for the photovoltaic application. So I will conclude my lecture by this part. Okay. Basically, starting from my PhD, I was involved in electrolytic theory and electrolytes and battery fabrication, supercapacitor fabrication. And for this optical properties, this work and the theory is also new for me. But I'm always a student to learn new things. So I'm ready to learn details about this solar cells or photovoltaic applications, for which I have to use this DFT. Now let's compare this experimental material research and how it is difficult with compared to this computational. So as an experimentalist, try to think the answer of the following terms. So I'm just I have mentioned I am also the experimentalist, so I face the same problem starting from a PhD work. How many methods of preparation you adopt for material preparation? Because the output, the result, this depends on the methods of preparation. So single material, it is prepared by different.
सर अनम्यूट हो गया, म्यूट हो, सॉरी म्यूट हो गया, म्यूट.
Okay. अब ठीक है? Sound is okay?
Yes, sir. Yes, sir.
I proceed. Okay. So that how much time you take to prepare your materials. So for the experimentalist, the time is very important for the preparation of materials. Many materials, it takes more than 24 hours to prepare. Can you gauge the cost of material prepared? Cost is also very important parameters. As far as the research in India is concerned, this is very important. And for characterization studies, list out the method of characterization of your sample. At least 3 to 4 characterization methods we adopt in our experimental works. Is one important question is all tools or devices used for material characterization is available in your institution? Because for characterization, if you use the instrument from other labs, then how much time gap is there to prepare of materials and its characterization? Some just apart from that, composite materials, the glassy materials and other materials, the stability is very important. And if you prepare a material and the characterization is not done in the same time, then there may be some change in the result showing by that characterization tool. So the gap between preparation of materials and its characterization studies, this is very important. So all characterization results predict the similar behavior of your materials. You have to you are using 4 to 5 characterization methods, and all results are supporting, then it's a good one. So all these are the terms which we face during our experimental work, and I'm also facing the same here. And when we compare with this experimental result and find the tool that is one new field that is known as the computational material science, and this is actually the powerful partner to experimental and theoretical studies in all sectors of sciences. The computational approach, that it may be that DFT or that MD stands for molecular dynamic, may become the only way to handle materials under extreme conditions that never be reached in laboratory in time-saving and cost-effective approach. So when we compare with experimental, then this is very time-saving and cost-effective approach. For example, that investigation of geological that material presented the earth potential materials at high pressure and high temperature. This is one example. And interaction energy and transition states during chemical reaction perform over catalyst. So this is a different computational method, and that with time scale and length scale, and that DFT, which is the quantum mechanical based studies. This is in this region, and up to that continuous model to that in millimeter scale. So this is that scale terms, time scale as well as length scale. So that computer experiment, which is also known as the molecular modeling, because we are modeling, we are studying the materials up to the molecular and now as electronic level. So this sometimes experimentalists or many persons think that the molecular modeling is a animation type game, but this is not true. The molecular modeling is not a computer game based on animation. This is actually the bridge between theoretical and experimental result. This molecular modeling is a new frontier for design and a discovery of new materials. This enables the process to become considerably quicker and cheaper. So by using that desktop on everything on a screen of computer, you can design the materials quickly, and also just with a very small span of time. This is a crystal clear objective to better understand and predict the properties and performance of novel or complex materials and the devices. Molecular modeling focus overall understanding the interaction between atoms or the group of atoms. So it is flexible, and whatever you want, you can perform using the computer tools. So this density functional theory, this is a vector in material science. The electronic structure calculation, which is subject to density functional theory, can play an important role in the discovery of new materials. For example, this topological insulator, which is whose surface is metallic and that material is insulator, it is first discovered by using density functional theory. So it is predicted first by theoretically, then it is experimentally analyzed. Now that DFT is electronic structure theory, the behavior of electrons in the material and how they are distinguished in real space and in different energy levels from the main subject of the electron band structure theory. It determines its cohesive energy. And by using this electronic structure-based theory, we can find these transport properties, optical properties, electronic structure, magnetic properties, and that catalytic properties. So for chemistry as well as the physics person, material science person, this theory is very important. Now, so let's go through that evolution of electronic structure theory. So generally, when we talk about electronic theories, then we start from this theory given by Paul Drude and Lawrence, and starting from 1900. And in this, it is assumed that the metal contains free electrons, and that moves in the background of positive ions. And this, then there is a concept of that mean free path, relaxation time, etc. And This approximation is known as independent particle or one electron approximation, and but this Drude model, this not consider electron ion interaction, electron electron interaction, and electrons are assumed to move and independent particles. So just we compare this kinetic theory of gases in this model. Pros and cons of this model. This model helps to understand some properties of matter such as conductivity of materials, but it is fails to explain the specific heat at low temperature. Then that Sommerfeld has modified this Drude model by including that Pauli's exclusion principle, or that by including this Fermi-Dirac distribution function, and explain the specific heat of solids at low temperature, and this Weidmann-Ferret model. And failure of this Sommerfeld model, this is predicting explain mainly other properties, including why some materials are insulator. It is not explained by this model. And then the next attempt was made by Bloch in 1928, when that system is taken as a periodic function, that crystal is taken as the periodic function of that. So this applies a constant on the form of electronic wave function and defines a quantum number k, and this is that Schrodinger equation. And this Schrodinger equation is used to used for the electron moving in the weak periodic potential. And that concept of band structures, EK diagram, this was given by Bloch, and it is used to understand the behavior of material. Then this evolution of that electronic structure theory in the next step, and on the basis of this Bloch theory, if the number of electronics material is such that the bands are completely filled, then that will behave as insulator. And if this gap, this is EK diagram, if the gap is less than 2 electron volt, then that is semiconductor. So this is because it could be have small conductivity room temperature due to thermal excitation of electrons across the band. So this is for the nearly free electrons in the matrix, and this is for the crystals, and where for the localized electron, this EK diagram, and well given in simple solid-state physics book. For the many body problem, many particle problem, what we know about this Schrodinger equation, this is exactly solvable only for the 2 particles analytically, and very few particles numerically. But for the real-time solid materials, for example, the number of electrons in nuclei in a simple pebble is about 10 to the power 23. So the solution, that equation, solution of Schrodinger equation, this is not possible. Then we use several approximations. This is simple Schrodinger equation, that the function of this position for n number of particles there. Then we talk about different kinds of interactions in solid materials, and if we have that electron-proton, electrons in one atomic system, then we talk about the kinetic energy of electrons and the nuclei, and then the repulsive Coulomb interaction between pairs of electrons. This is represented by this relation, and this half term, it is divided by half because I is not equivalent to J. Electron does not repel each other itself. And then this repulsive Coulomb interaction between pairs of nuclei. So the pairs of electrons, pairs of nuclei, and that interaction between that electrons and nuclei. This all these are given by different terms. So as a whole, this is the Schrodinger equation of many body problem, which is the sum of these 4 parameters: this T, kinetic energy of electrons, and this potential term for nucleus, and this is for the electron interaction, and this is for the electron nucleus interaction. Right hand side is the total energy. And this directed density function theory, this is very efficient and general, but during with a good approximation. So in order to get in order to cover that generally of that density function theory, it is starting from this Born-Oppenheimer approximation, in which that nucleus is very heavy. When we go through this cartoon, this elephant, this is nucleus, and these are the electrons. So the mass of neutron, nucleus and electron, when we compare, this is much greater than 1. And the velocity of electron, when we compare with nucleus, this is much greater than 1. So nuclear are much slower than compared to these electrons. And this time-independent Schrodinger equation, we consider this. And we solve the Schrodinger equation by using that method of separation. So all these are some quantum mechanical terms. So in order to understand the density functional theory, the prerequisite is the student must have the basic knowledge of this quantum theory, that Schrodinger equation, etc. Then this BO approximation, this is also good for the exact solutions only for one electron system, just for example hydrogen. But when many electron systems or many body systems are used, then there is also some problem. So this is divided in two parts. One part is this ionic part, and the second one is that electronic part, and these are the equation. So this is suitable for semiconductors and insulators because ionic motion does not affect the excitation of electrons. So this model, this approximation, this is only suitable for semiconductors and insulator, and this is not suitable for metal because the metal band gap is 0. So this has limited use. Now, next step is the idea given by Hartree, and in this idea, so that material, in spite of that many electron system, it is converted into one electron system. So in place of taking different electrons, so that electron cloud or electron taken as a liquid in terms of electron density is used. So this in Hartree's idea, this reduces many electron problem to one electron, known as one electron approximation. This many body Schrodinger equation with this spin, this Hartree's approximation. So this is that equation, and here the solution given by this Hartree, it is the multiplication of different wave functions, psi1, psi2, psi3, and so on. And this is the function of that position as well as the spin, and that probability density term, it is also used, that psi I squared del S square psi to interpret that charge density. So I'm just skipping some mathematical terms, so that Hartree potential term, it is introduced by Hartree, but this approximation, this is only for some. This depends on. Just the Hartree potential depends on the solution itself. To solve this, a case is made for this VH, and the Hartree equation is solved. By using this solution, VH is computed and equation is solved against the potential is computed. This procedure is repeated until the input and output potential are very close. This is a self-consistency method, the term. Within some tolerance, this procedure is known as self-consistent procedure. And negative of this for one electron theory, electron moves as an independent particle, and such theory does not include the effect of correlation of electrons. So electron is taken as independent particles. So the interaction between electron, it is avoided. It includes the electron-electron interaction only in an average manner. So not taken as so many body Hartree wave function violates the anti-symmetric requirement, and this anti-symmetric requirement is further included by this Slater and Folk, and now the method is known as Hartree-Folk method, and this is that anti-symmetric term, it is included here. And the first time this Thomas Fermi, we have introduced that electron density term, and the basic idea is to describe atoms, molecules, and solids in terms of electron density, which is further applied by Consum, and these are the terms used by solid state physicist, and that Quenberg theorem, it is given by 1964, and here in place of the wave function in that Schrodinger equation, it is replaced by charge density term, and It is that HK theorem, and these are two theorems. First is theorem 1. The external potential here is the unique function of the electron density, and as a result, the total ground state energy of a system is also unique, the functional. Remember this, that generally we talk about that energy at the ground state, and that density functional theory based studies are ground state based studies. And theorem 2, the functional En for the total energy has a minimum equal to the ground state energy at the ground state density. From the first theorem, electron density Nr, this is the function of R, associated with the ground state corresponding to the external potential Vr, cannot be reproduced the ground state density corresponding to different Vr. And this follows that the ground state electron density is determined Vr uniquely. The further implies that Nr is produced by unique this Hamiltonian. And this is the equation, that theorem. And this is the energy term, which has two terms. One is related to this external potential, the second is this function. And this functional is the sum of the kinetic energy of non-interacting electron and the gas density, and it's at ground state. And second term is related to classical Coulomb energy, and third one is this exchange correlation function. So the exchange of this electron, this very important term, it is introduced by this Coinberg. And this is further just some further terms related to this quantum equation. And this Vxc, this is known as exchange potential, and Vh is the Hartree potential, and this is that external potential. Now this is that equation, which is now similar to Schrödinger equation, and this equation is solved, and thus this would give us the electron density Nr, which is in turn would give us the total energy E. But still there is two problems. One is the functional Ts is not known. Second, Vx is also unknown, and he has introduced that arbitral terms in this. Mohan has introduced that arbitral terms in DFT, and this is that equation that is similar to the Schrödinger equation. This equation is known as Mohan equation, and through which he has bagged the Nobel Prize in 1998. Now, DFT as a glance. So this is that major journey of development of the DFT, starting from that electronic model to this Nobel Prize winning by this that Walter Kohn, and these are exponential growth in this DFT based research, and this is also known as ab initio, and which is actually Latin terms. What it means is it is from beginning, so we start from zero, and it is also known as the first principle terms. And the method solely depends on the law of nature, that is the quantum mechanics. And one good thing is it does not require any empirical parameters. So this is the first principle calculation. This is a bridge between theory and experiment. And one important term here, generally all DFT persons mention that the computer is actually a dumb box. So before working with the computer, giving some data to computer, you have to think twicely and give good information to that computer to calculate. Otherwise, you will waste much time and you will not get you will get nothing. Some key points: DFT is a description of interacting electrons in the ground state, this including exchange and correlation, and the basic variables in the density rather than the wave function. So this wave function, this was used by Schrödinger. So in place of this wave function, density is used. The theory is simple and the implementation efficient compared with other methods. This is cost effective, so this is simple, and implementation scales at least as n square. It offers an excellent balance between this, one of the important point. It offers an excellent balance between accuracy and scale of calculation. Many times that general person, the core experimentalist mention the term, "Oh, you are doing DFT, man, this is just the rough work." But no, this is now not true. We have some strong correlation functions and the tools, then good and accurate results are predicting given by DFT persons. This is a self-consistent process. Generally that start as an initial guess of that wave function psi, and then this charge density is calculated, and this Vx is calculated, and by putting this some equation, new density is obtained, and then this is compared with the initial one, and using different iteration, when we get that charge density up to our desirable requirement, then the final energy, forces, and other parameters were calculated. So this is the self-consistent process, and this VXC, which is known as that exchange correlation potential, and generally that local density of a state or general gradient density of a state is used. Now the pseudo potential. So where we have to give all the informations to computer system, so that computer system we provide all the informations related to materials in atomic, electronic level, and that is in form of the pseudo potential. So this pseudo potential, this is to replace complicated effect of non-valence electrons. So generally we mentioned that the electronic various properties are the periodic function of valence electrons, but we also consider that non-valence electrons, since that the effect of nucleus also, and that the combination of these two as effective potential we use in pseudo potential. So these pseudo potential are further divided into norm conserving and ultrasound. Depending on different tools, we use that suitable pseudo potential. This is local density approximation, the correlation function. So assuming that the exchange correlation energy density is very poor, every position in the space for the molecule is same. So this is for the rough calculation, you can use this LDA. And the second one is that generalized gradient approximation, and this good with compared to that the first LDA with good result. So for different quantum chemistry program, this offers a vast variety of choice of functionals. So many functionals are there, and before starting or before using that functional, you have to think twice. So how we are using a good functional for which you have to just follow these points. First of all, you have to search the literature for calculation on similar materials and properties. Many more properties than just the energy can be computed from DFT. Compare your candidate functionals by searching the publication that describe their development for their strength and weakness. So you have to compare, you have to study the weakness as well as the strength of your functional you are going to use. Find out how your candidate functional perform the different basis sets. So what is the summary of this particular page is, before using any instrument, we calibrate that instrument in experiments. So similar thing, that calibration term is here performed on the basis of choice of that proper pseudo potential as well as that exchange correlation functions, etc. So this is actually the calibration part. So before going to the details of that study, you have to take care of during the choice of this functional. Some applications. So applications, this is applies to atoms, molecules, polymers, surfaces, and periodic structure. And you can get that self-consistent total energy, forces, stresses at the ground state. Structural optimization, you can get optimized structure, elastic modulus, mechanical properties, electron band structure, many-body system, phonon frequencies. So for the dynamic stability, to check that dynamic stability, you can phonon dispersion, electron phonon interaction, optical properties, transport properties, surface analysis, etc. So these are different applications, and in my laboratory, we have performed several computer experiments and get good results. So I will show in the forthcoming slides. These are some good DFT codes, and depending on types of methods adopted, these are good DFT codes, and some of them are partially available that require fund, and many DFT tools, these are free of cost. So in my laboratory, I use Siesta. Generally, this is Siesta. This is free software to use. And, in my laboratory, tools for designing visualized materials and nanomaterials. Generally, we use all these terms. First, before going to the details of that materials, I search or suggest my student to search materials using that material project link. So by using this material project link, you can get the structure, about the structure information. That material is new, or someone has developed that materials before. So most of the materials that is given in this material project, that was checked by WAS commercial tool similar to that system. And for material designing and visualization tools, in general, in my lab, I use Avogadro. This is all the tools I'm using here are free of cost. So this is a good material editor and visualization tools. GDIS, this is a command-based tool, and this also good material. Vesta, JMOL, Argus Lab. So for homonomer plot, you can use this Argus Lab. This is for the biomolecules, especially for polymeric materials, especially that molecule for molecules. Nanotube modelers. Many times a student asks me, sir, how we can generate that nanotube or that nano ribbon, and just I mention this nanotube modeler. So you can search and get this. Molden is a good tool. And this is for the visualization. And excretion, this is to plot charge density. Good visualizer. And this ATAL virtual nano lab, this is commercially available tool. This is for the material designing, as well as this is actually one separate software to perform transport properties and various electronic properties. Good tool, window based as well as Linux operating system based. And plotting tools. So XMGray, this is a good plotting tools. One can use that MATLAB and GNU plots, etc. MATLAB is a commercial tool, so I prefer XMGray. So these are the tools we are using in laboratory, and anyone can use free of cost on this, except this MATLAB and ATAL-FDP-OMAD. So some results from my lab. As I have mentioned, for every type of materials, we can use this DFT based tools. So whatever result I am showing here, all these are studied using Siesta, that tool. So this is that crystalline materials. Here that this is band plot, density of states plots, and even that optical properties I have mentioned here, and, published in a good journal. So how this optical properties it is obtained, this will be detailed by Dr. B. Kishore tomorrow, and I am not going to detail here. Although that for the solar system or photovoltaic devices, the study of optical properties is very important. So especially that the absorption of that light, it is studied for that solar system. So the study of optical properties is very important. This is the second crystalline material. So first one is also crystalline materials, and this is one composite of silver and copper. And one beauty of this density functional theory is you can replace each and every atom of the system. So the transformation from silver iodide to copper, it is performed in different steps, and this is that optical property. And the shifting in this optical property, it is observed when we substitute this copper, replace silver atom with copper, and this beautiful result is obtained. Now one can study that buckyball type structures. So carbon buckyball, this is the famous material studied first in the buckyball structure. And now several studies in different buckyball materials are reported. So here this Jadeno buckyball and interaction of this buckyball with the graphene is shown in this particular paper. And here again I have performed that optical properties. And one can study that single chain of atoms can be studied. So this is that the function study of hybrid HB and graphene, the atomic chain. So by replacing that two atoms of PN with carbon, and the change is observed. So that change in electronic properties, it is reported in this paper published in Physica E, and that is also in two-dimensional case. That was the single chain, and this is now two-dimensional, and the studies as a function of thickness is reported here. And then that monolayer, nowadays the monolayer type term is used by density functional scientists. So this is that monolayer, and that the TIN HFN materials. And again, the transformation of one structure to another structure, it is reported in this paper. We have also observed that magnetic properties in these materials when we just transform from this TIN to HFN. So for this magnetic properties, that up spin and down spin, it is used. Then gas sensor. So as far as the device is concerned, for the sensing device, you can use that density functional theory based tool, especially that Siesta and related tools. So here, in presence of and absence of that gas molecules, the change is observed. If there is a change, means that system is sensing that molecule. So good gas sensors are theoretically analyzed by using this DFT. This is another monolayer, and that SN2 monolayer. Again, for the sensing purpose, this particular monolayer is used. Also, the surface study can be performed, that HTM type analysis for graphene and silicon. This is not my work, just to show the capability of DFT I am including here. Now, polymer-based studies can be performed by using this tool. So, as I have mentioned, that initially my studies were concentrated to electrolytic type behavior, where we use polymer electrolytes. So, our main target, that was to enhance the conductivity of that particular polymer electrolytes. So for which we just use some salts and insulators to that polymers and increase the conductivity. The mechanism, how in presence of that salt as well as that insulating materials, insulating crystal, that particles, how that conductivity is increasing, that theoretical part is analyzed using this in this paper. So the influence of this glycol and this plasticizer with this PONI complex, it is represented here. So the interaction of salt and the polymer chain, this is showing you. So as well as that mechanical stability, because the experimental persons, what I am observing is they are giving good result related to electrolytic properties, conductivity and that structural properties, etc. But the mechanical strength, this property is avoided in general. So in this theoretical studies, we have studied that the role of this interaction and the mechanical properties of that polymer. So this is that plot. Another polymeric materials. So the effect of this salt in this polymeric chain and its electronic properties as well as the mechanical stability is so. So this is one of the important material, that is the ketoshan, and the transport properties of ketoshan is shown. And we have observed the effect of twisting, molecular twisting in that ketoshan. This is the good result. So when we rotate a particular monomer along the axis, result is seen. And this is one step towards that medical physics, where the effect of non-essential protein on D-glucose to control diabetes, it is studied using that DFT approach. So this is our recent publication. Moreover, some thermal properties with the help of other tools, just like Gibbs 2 and Photovoltaic, one can get thermal properties also. And that the battery performance can be studied using that optimization of the system. So these are equation one can use. So as a summary, I can say that that DFT based tool, these are a good tool to study various materials properties. Almost all type of properties can be analyzed, and we can help the experimentalist to give the details of the mechanism of the system. If you have a good experimental result and you want to explain why that particular result is being shown by that material, then we can use DFT to predict that behavior. Now the next segment is computer experiment with Siesta. So this is a very easy tool that so computation using Siesta. This is the full form of Siesta is Spanish Initiative in Electronic Simulation with thousands of the atoms. So this is well documented the page of the Siesta. Why Siesta? This is a method as well as the computer program implementation to perform efficient electronic structure calculation and ab initio molecular dynamic simulation of the molecular system. This Siesta efficient comes from the use of strictly localized basis sets and from the implementation of linear scaling algorithm, which can be applied for the suitable system. This is very important features of the code is that its accuracy and the cost can be tuned in a wide range, from the quick exploratory calculation to high accurate simulation, matching the quality of other approaches such as plane wave and all electron method. These are the other methods. So here we use that superposition method, and this is efficient enough. The possibility of treating large system with some first principle electronic structure method has opened up new opportunities in many disciplines. This Siesta program is distributed. This is free of cost and has become quite popular and increasing use for the researchers in especially that geoscience biologists and engineering students also. And currently there are several thousands of the users all over the world are adopting this method. And this is very simple to learn. One thing is it is cost effective, it's fast with compared to other tools. This is very simple to learn. So if you study, you want to learn a data system, just you need one laptop. Minimum requirement is if it's i3, it's sufficient. RAM is minimum 4 GB. If you have 16 GB, this is good, good. But the RAM, you can start from this 4 GB for 10 to 12 atoms. You can study this. Then operating system, obviously you need to Linux operating system. So the working knowledge of Linux operating system is important, and that easily it can be learned easily. Now today this is the age of YouTube, so just make Google as a good friend. Internet facilities with sufficient speed is also important, and the basic knowledge of solid state physics and the material science. So one can start using Siesta. And to run system, what we need, we obviously, just as I have mentioned, that we have to give all the information to the computer. Then that information, for that information, we give that input file. So first, you must have that tool system, and one can get free of cost using internet, and then one input file, and that FDF file. This is very flexible, and that pseudo potential. Yes, I have mentioned that pseudo potential. All the information inside that pseudo potential, and this is the typical example of an input file. So in input file, what we give, we just give the name of atoms, number of species, and by using with the help of basic chemistry, one can get all this information, and then the coordinates of the structures of that system. So when you design that material, then you need to get this coordinates of that atom, atomic coordinates. So the position of that here, this is water. So the position of the hydrogen atoms are mentioned here by using 2, 2, and 1. 1 is this oxygen. This is well documented, so you can get manual in the website. Some very good tutorials are there in the website, and one system adding list is there. So if you have any queries, any doubts, any problems, then you can just post that problem in this mailing list, and you can get the answer from there. And beginners can start from this channel. This is my channel, and many beginners are starting using Siesta from this. So the lecture from 1 to this now about 29, 30 videos are there. So how to install that Linux operating system, how to prepare that input file, and different properties, how one can study that different properties. All these are listed in this channel. So about 899 subscribers are there in this channel without any insisting. Just do not just subscribe this channel. So just I avoid such type of things. But the subscriber are 899, and all these are self-motivated candidates, and using good and getting good emails. Now, frequently asked questions. May I learn the material modeling? Even though I don't know much about computer, yes, one can, because you can easily learn. I can only work on Windows operating system, so Linux operating system, the learning Linux operating system is not difficult. You can easily learn, and we just use some commands, not all the one. I don't know how any programming language, no need of knowing programming language. But if you are familiar with Python, or if you are learning Python and Fortran, then this will help you to understand that behavior of that system. And are the materials modeling software freeware? Yes, okay, or not all, but this is the freeware. And is there any window-based tools also? There are many window-based tools also, but maximum window-based tools are commercially available. Free of cost tools are in general absence in Windows. So to start that molecular modeling, start reading good books, solid physics, fundamental quantum physics, chemistry, density functional theory, and learn working up on that Linux operating system, and follow the method I have adopted in my channel. So you can easily learn. So within 1 week, maximum 10 days, you can get you can learn Siesta up to a particular level. Now the solar cell, and Professor Khare from NIT Raipur have given a wonderful lecture on this solar cell. So I'm not going to the details of this, but generally it is an electrical devices that convert the energy of the light directly into electricity. This also known as photovoltaic cells, and these are the principal types of solar cells. So all these have been detailed by Professor Khare. And the working also, the simple thing is that light is absorbed, and that electron hole pair is generated, and via generating this electron hole pair, that operates, the solar cells operates. These are different configurations of the solar cells and different layers, starting from this glass to different materials. And depending on the materials of this active region, there are several types of solar cells are there. So these are different types of solar cells and quantum dot based solar cells. So beautiful pictures, even in internet. And so these are different sources, and which has been detailed by Professor Khare. And the efficiency is very important. So that DFT based study, this is that accuracy, different accuracy of solar cell. So in the DFT based study, what for this solar cell system? So for the solar cell system, we have to study different materials, and especially the optical properties and electronic properties of material that can be studied by the DFT. So if anyone want to study that solar behavior of that material, so before going to that tools related to solar cells, one must have the knowledge of that DFT, and by using that DFT, the optimization of the system, it is important. And after optimization of the system, that optical property is important, along with that band structure and density of states, etc. And then it is used by different tools. So these are the different materials. So we have in my laboratory, we have studies PS3T, and some chlorophyll we have studies in my lab. And now free photovoltaic softwares. If yes, I have mentioned, you must be the good friend of Google. So free software, just search a free software using Google for the solar cell designing, and you will get a wide list. And in some softwares are Linux-based softwares, and the maximum softwares are window-based software, and good window-based softwares are commercially available. So in my laboratory, that GPVDM, the general purpose photovoltaic device model, we are using this, and you can get maximum software using depending on the types of materials you are going to study. And this is layout of that general purpose photovoltaic device model. So different layers are there, and you can start that new simulation, and you can study different characteristics. So this is fast enough, so you can try this. And what we provide to this software, generally maximum models are ready-made in that software. Almost all the softwares, ready-made structures are there depending on different types of materials, and you can change the parameters. So if generally this particular software, this requires the absorption of that energy. So if absorption of that materials, so if you have that particular absorption value available experimentally, then you can use that experimental data, or you can get that data, that absorption data by DFT also. So before going to that detailed fabrication of solar cell devices, solar cells, you should theoretically study. I just suggest you should start theoretically first, just to design that material, optimize that material, study its optical property, and using that optical parameters, use one suitable software related to that photovoltaic cells, and give that data to that system, and start studying that characteristics, that efficiency, as well as other IV characteristics, etc. And then if you get a good result, then go for experimental studies. So generally, experimentalists are using such type of process before going to laboratory level. So what my suggestion is, start for DFT, study that material. So for the details, how that particular material is optimized, all these are mentioned in my channel, and you can mail me also. And then after getting optical properties and electronic properties, use that data, and for the suitable softwares available in internet, some are online and some can be easily installed using Windows operating system or Linux. And then after analyzing the performance, theoretically go to the laboratory and get desired that device. So the final slide, this is with this message: please save electricity, save water, and save oxygen. That is very important. Thank you all.
Thank you so much, sir.
I
Now the
think it
session is
was
open for
too
a question.
exhaustive. Was too exhaustive. Any questions?
Yes, now the session is open for a question answers round. If any of the participants want to know more about the DFT.
My lab is open for learner. I'm also present in Dr. Pandey's, Ravi Pandey's lecture. What we generally prefer, we just ask for people to do work. Yeah. Ask questions and ideas and proceed your work. You can share your materials and we can discuss about that materials. So I try to explain all the terms. In the case of any queries, you can message me also. You can search me in YouTube, that is Mohan L. Verma, and you will get my channel, or you can mail me. Your queries, your interest, your collaboration request, via this. No question? मतलब किसी को समझ में नहीं आया थोड़ा जा
नहीं से सबको समझ में आया होगा, that's why all doubts are cleared.
Hello, sir. Good afternoon.
Yes.
Sir, I am working in perovskite solar cell. Can I use GPVDM for studies theoretically?
Yes. Good tool is there. I have just go through this Windows-based tool, and you can start.
Okay,
Very
sir.
good. It is included there. I have seen.
Okay, sir. Do I need some basic knowledge like solid state physics for using this tool?
You should
Written
no.
in
You,
slides.
no. You should know about the fundamentals of your solar cell. If you are already working in the solar cell, then you can start, because the different layer material, different materials, about materials, and the details of theoretical solid-state physics is not needed. Just you have to click, change the data, change the parameters, and if you have that experimental result, then you can put that experimental result to this software too.
Okay, sir. Thank you so much.
Thank you so much.
And good tools are also there. Just I have given this example, and you can also search some good tools internet for this particular source. So many softwares are there, and most of the softwares are free of cost.
Okay, sir. Thank you.
Thank you, Nitika ma'am. Anyone else? Okay, sir had already shared his mail ID. So if anyone wants to know or anyone wants to have a query, he and she can mail the question at that particular mail ID. Thank you so much, sir, for giving us such a valuable information about the DFT. Thank you once again.
Thank you all for your patience. I think now I should leave. Thank you.
Yes, sir. You can, sir. Thank you, sir.